Hello everyone, my name is Bin Yang, a research scientist at Uber ATG. In this session, I provide an overview on works that tackle 3D perception for self-driving. 3D perception is a fundamental task for self-driving, as it provides safety estimations of surrounding traffic participants for downstream prediction and planning tasks, and therefore has a large impact on the performance of the whole autonomy system. It's also a challenging task in that we have to process high-dimensional data from different sources, produce accurate estimations by exploiting all complementary information, and do all of this in real time. This session is organized by different input data modalities: LiDAR, cameras, radar, and HD maps. We'll begin with LiDAR-based perception algorithms. In particular, we'll discuss different LiDAR point cloud representations, how to exploit their sparsity to speed up computation, and the predominant detection frameworks that currently exist. We'll then move on to approaches that perform 3D perception using a more affordable sensor, cameras. Afterwards, we will talk about sensor fusion techniques that jointly process LiDAR and camera data, as well as radar data. Apart from multiple sensors, we can also exploit prior knowledge like high-definition maps to improve the system robustness. HD maps are built for various purposes for practical self-driving systems, and here we discuss the use of HD maps in the context of 3D perception mainly. Lastly, while in most perception algorithms focus on a few predefined object categories of interest, it's also critical to driving safety that we recognize unknown objects on the road, like animals and garbage that interfere with our driving route. We therefore briefly discuss algorithms that address this open set perception task. While in this session, we will try to cover the following commonly used sensor modalities for 3D perception. We'd like to emphasize that there exist other sensors for this task as well, like ultrasonics. Please see session 1 for a more comprehensive review of hardware for self-driving. We first revisit LiDAR-based approaches and begin with different representations for LiDAR point clouds. Overall, there are two main types of representations: voxel-based and point-based. Voxel-based representations discretize the point cloud into uniform grids for easier data processing. These grids can live in the original 3D space or in a 2D space that's projected from 3D. Two common 2D projections are the range view projection and the bird's eye view projection. On the other hand, a point-based representation keeps the naive, irregular structure of point clouds free from discretization errors. One of the most commonly used representations for point clouds is 3D voxels, which discretizes the point clouds into uniform 3D volumetric grids. Different voxel representations can be applied, from simple ones like occupancy value to more complex point features that are learned from data. 3D voxels preserve the 3D metric space and enable effective multi-scale feature extraction with 3D convolutions. However, as computation and memory footprints grows cubically with regard to detection range and voxel resolution, this creates a trade-off between accuracy and efficiency, since long detection ranges and fine-grained voxel resolutions to capture the details of small objects like pedestrians are necessary to build robust perception systems. What's more, the 3D voxels themselves are very sparse for LiDAR point clouds, which means that a large proportion of computation is wasted on empty locations. While 3D voxels are very sparse, the 2D range view projection is a much denser and more compact representation of LiDAR point clouds. This projection works by mapping laser beams in horizontal and vertical directions to a 2D image plane defined by the LiDAR field of view in azimuth and elevation angles. The resolutions in azimuth and elevation are usually set according to the LiDAR specification. In other words, one can understand the 2D range view projection as a panorama image for LiDAR. Commonly used pixel representations are point height, range, and occupancy. Range view projections can be efficiently processed by 2D convolution, and they also preserve full range information without range cutoff as in 3D voxels. However, it is more difficult to incorporate priors here due to the metric space distortion, and the neighborhoods in the range view are not the true ones, which makes 3D learning less straightforward. Another 2D representation is bird's eye view projection, which works similar to 3D voxels, but consolidates height information as a BEV voxel feature. These BEV voxel features can be either hand-designed, such as statistics at discrete height slices, or learnable features or points within the BEV pillar. BEV representation shares the same advantages as 3D voxels in that 3D metric space is preserved, with the additional benefit that the spatial dimension of feature maps is reduced from 3 to 2, leading to more efficient inference. Note that this is a reasonable assumption as planning is performed on the same ground. However, the computation and memory costs still grow projectically with regard to voxel resolution and detection range. Later, we'll discuss techniques that exploit sparsity to speed up computation. While previously introduced representations all discretize the irregular point clouds into regular 2D and 3D grids, we can also use its raw representation as an unordered set of 3D points, where 3D coordinates are used as a point feature. We then apply point-based neural networks for feature learning. Unlike grid-based representations, the point set representation doesn't have discretization error, as precise point locations are preserved. As a result, this often leads to a better object localization precision. The drawback of this representation mainly lies in its point-wise feature learning. In particular, this representation creates significant computation overhead for irregular memory access and dynamic kernel computation. What's more, multi-scale features are often desired for object detection, and this is realized by key point subsampling for point-wise feature learning. However, different key point subsampling strategies can affect the final performance a lot, due in part to the dramatically varying point density of LiDAR data. So far, we've reviewed 4 different representations for LiDAR point clouds, 2 of which are very sparse, 3D voxels and bird's-eye view projections. A natural question arises, can we exploit the data sparsity to speed up computation? The answer is yes. We can use sparse convolutions to avoid wasting computation on empty locations. Sparse convolution works by doing computation on valid locations only, and valid convolution is realized via the image-to-column algorithm. The valid locations are stored as a lookup table beforehand so that the sparsity pattern doesn't change as we stack more convolution layers. While sparse convolutions can generalize very well, it produces a limited speedup in the 2D case, as the image-to-column algorithm doesn't run as fast as the well-optimized 2D dense convolution kernel. To address this performance issue, sparse block convolution is proposed. Instead of operating on original valid locations, it first approximates the sparsity mask with a blockwise mask, and therefore is able to exploit the faster Winograd algorithm for dense convolution on all blocks. The weakness of the approach is the introduction of a tiling step, which is unsuitable for very scattered sparsity patterns. However, in the case of self-driving, where we care more about on-road perception, the drivable region can serve as a sparsity mask, and it can be well approximated by blocks. Here we show a video where we apply sparse block convolutions to speed up bird's-eye view vehicle detection. On the top are the results of the original dense BEV detector, which detects vehicles within 70 meters range. On the bottom left, we show the results that exploit the drivable region as a sparsity mask, where we can achieve about 2 times speedup. On the bottom right, we show the results that exploit the sparser mask produced by a segmentation network, where we can achieve even more speedup. It's also worth noting that the speedup is achieved without sacrificing detection accuracy. In practice, we observe less than 1% drop in average precision. So far, we have discussed the various point cloud representations, as well as how to build efficient feature extractors on top. Now we will briefly discuss different designs of the detection framework. In the domain of well-studied 2D object detection, there exist 2 different frameworks, which are one-stage detectors and two-stage detectors. While one-stage detectors produce pixel-wise object estimations through a single forward pass of a 2D ConvNet, two-stage detectors decompose the task into 2 steps. First, generate object proposals, and then refine them based on region-specific features. When it comes to 3D object detection, we can apply the same 2 frameworks as well. We first review the one-stage 3D object detectors, which produce dense 3D detection outputs in terms of box information and class probabilities on the last layer of a ConvNet. For 3D object estimation, there are 2 ways to do this. One way is to directly regress the 3D size and orientation of a bounding box at each pixel of the output feature map. This means that we believe the network capacity is large enough to capture the variations in object shapes. Another solution is to resort to a set of predefined anchors or prototypical object shapes. For each output pixel, the model predicts the probability for each anchor, as well as the residual information with regard to that anchor shape. As a result, the issue of large object shape variance is remedied to some extent. One-stage detectors typically have real-time inference speed and have fewer hyperparameters to tune in general. However, they suffer from imprecise object localization, as in many cases, we are estimating the object boundary from the center pixel alone. Two-stage 3D object detectors, in contrast, introduce the concept of region feature pooling to further refine the initial object estimations. While the first stage is almost the same as one-stage detector, the second stage takes high-confidence detections from the first stage and extracts region of interest features for box refinement. In practice, you can add even more stages afterwards for more iterations of refinement. Two-stage detectors have achieved the state-of-the-art detection accuracy on many public benchmarks, showing advantages over one-stage detectors, especially in terms of precise object localization. However, this higher accuracy is achieved at the cost of slower inference and more hyperparameters. So far, we have reviewed LiDAR-based approaches for 3D perception, covering different representations, efficient feature computation, and different detection frameworks. Next, we'll talk about camera-based approaches for 3D perception. Cameras are appealing in that they are much cheaper than LiDAR, provide textual information that LiDAR doesn't have, and capture more fine details. The main issue with cameras is that we lose depth information, which is important for 3D perception. In order to reason about 3D from the 2D images, we need to lift the information from 2D space to 3D space. This can happen at 3 different places: input, feature map, and output. We first look at methods that lift to 3D at the output level, which directly predicts 3D bounding boxes from 2D pixel features. To bridge the gap between 2D features and 3D targets, several techniques have been proposed. From the perspective of feature learning, one can add 3D LiDAR data as input during training and regularize the 2D image features to be close to the 3D LiDAR features in the feature space. At test time, we do not use the 3D LiDAR data as input. From the perspective of output parameterization, instead of directly predicting the 3D box, one can predict the object key points in 2D and solve for the 3D box via template matching, as shown in the figure. This type of approach can be considered as a simple extension of existing 2D detectors with a different output targets. However, the performance is usually unsatisfactory when measured in 3D space. Now we look at methods that lift to 3D at the input level, also known as Pseudolidar. These approaches first perform pixel-wise depth estimation, and then convert the image pixels with estimated depths to the 3D space following the camera parameters. Then an off-the-shelf point cloud-based 3D detector can be applied to the Pseudolidar point cloud. In these models, the depths can be inferred from monocular camera, stereo camera, or by self-supervision from multiple calibrated cameras or video sequences. Pseudolidar-based approaches achieve state-of-the-art results in camera-based 3D perception at the cost of an additional depth model. Instead of lifting to 3D at the input or output level, we can alternatively lift to 3D at the feature level in order to achieve a better trade-off between exploitation and computation. Specifically, a 2D ConvNet is first applied on the camera image to extract 2D image feature maps. The pixels in the 2D feature map are then converted to 3D space as a 3D point or array, depending on whether the associated depth is known or not. After feature map transformation, the resulting 3D feature map is then used to output 3D detections. Since the features lie in 3D space, they typically produce better 3D geometry. Another advantage is that the 2D 3D feature transformation only requires the camera parameters and can work even without depth estimation. The main weakness of this kind of approach also lies in the feature transformation. When depth is unknown, the one-to-many mapping brings ambiguity in the resulting 3D feature maps. When depth is known, errors in the depth estimation would also lead to misaligned 3D features. So far, we have gone through perception algorithms that rely on either LiDAR or cameras. Now we will see how we can combine LiDAR and cameras together for more robust perception. Broadly speaking, there are two main pipelines for LiDAR and camera fusion, the Cascade pipeline and the parallel pipeline. For the parallel pipeline, we further compare fusion mechanisms at different levels. For the Cascade fusion approach, a two-stage model is built. The first stage produces 2D detections from the camera image and converts these 2D bounding boxes into 3D frustums, given calibrated camera and LiDAR sensors. The second stage then performs 3D object localization, given LiDAR points within each frustum. This approach can take advantage of mature 2D detectors, which provide high-quality object proposals. Also, in the 3D space, the model only needs to solve the localization task instead of joint recognition and localization. However, due to its cascading nature, this approach cannot recover from errors made in the first stage. For example, if an object is missed by the 2D detector, it will not be able to recover by the second stage. Furthermore, 3D localization within frustums can be difficult for occluded objects. Now let's look at more widely used parallel pipeline for sensor fusion. We first review output fusion, which is adopted by many systems in industry. In these approaches, 3D perception is run on each sensor modality individually, and their perception results are fused together at the tracking level. Output fusion methods embody the spirit of modular design and therefore achieve redundancy safety. However, each object estimate is typically more unreliable as it comes from one single sensor, and the rule-based fusion is also error-prone. In contrast to output fusion that combines different sensor modalities at the most abstract object track level, input fusion combines information at the raw sensory data level. It works by converting different sensor modalities into a unified space and then combining them together. In the case of LiDAR and camera fusion, the unified space is said to be the 3D space as we care about 3D perception. To find a one-to-one mapping between LiDAR points and image pixels, we project each LiDAR point onto the image plane. If the point falls within the image, then the corresponding pixel is matched with the LiDAR point. Otherwise, the LiDAR point has no match. We then append the pixel features like RGB or predicted semantic label to its associated LiDAR point. The enhanced LiDAR point clouds are fed into an off-the-shelf LiDAR-based model. Compared with output fusion, these methods provide denser fusion of raw sensory data. However, they don't exploit camera information fully as it's represented in a primitive and low-dimensional format. They are also sensitive to unexpected calibration errors between sensors. A more promising direction for sensor fusion is to fuse at the feature level. Here, we can perform either coarse ROI-wise feature fusion or dense pixel-wise feature fusion. For ROI fusion, we project the same object ROI to 2D and 3D respectively and combine their features together. This is usually performed as the ROI pooling layer within a two-stage object detection framework. For pixel-wise fusion, the most straightforward implementation is to fuse pixel features with point features. The pixel-to-point correspondence can be found by projecting LiDAR points to the image plane. However, since LiDAR points are sparse in 3D, only occupied locations get complementary information from the camera image. To address this, we can add a learnable interpolation layer as shown in the figure that learns to interpolate the image feature at unoccupied voxels from image features at occupied voxels. The interpolation layer can be realized with continuous convolution, which is invariant to the number of neighbors and works in continuous space. After feature interpolation, we achieve a dense pixel-to-voxel fusion. Feature-level fusion fully exploits complementary information at multiple scales, and therefore is more robust to small calibration errors. However, as we need to perform feature extraction on each sensor modality first, this approach also brings more computation cost. We have reviewed the sensor fusion of LiDAR and camera. Now let's look at the radar and see how it can be used in conjunction with other sensors. Since radar is a 3D sensor, we will first look at how its 3D geometry information can be exploited. This usually happens in the setting of radar plus camera, which is a common setting for ADAS. In this setting, radar provides sparse but reliable 3D depth information for images. Many previously mentioned fusion methods can be adopted here, whether we simply treat radar data as sparse point clouds. However, the overall performance under this setting is typically not as good as LiDAR-based systems due to two reasons. First, radio waves cannot achieve the same ranging precision as laser light. Second, the radar measurements are sparser compared with LiDAR. Apart from the 3D geometry information, what makes radar a necessity in most self-driving sensor kits is its real-time and direct velocity measurements. Here, we discuss two approaches to explore the velocity information in the setting of LiDAR plus radar, which are the commonly used output fusion and the recently proposed attentional fusion. In output fusion, we perform detection and tracking from LiDAR and radar respectively, and then combine them together at the tracking level. Output fusion improves the system robustness by redundancy safety. However, the object state estimation is not necessarily improved, as they each come from only one sensor modality. Attentional fusion, on the other hand, addresses this by associating radar measurements with object detections, and then exploiting velocity information from the radar points to improve the state estimation of associated detections. Specifically, for each detection, we find its nearby radar points as candidates. We then convert the one-dimensional radial velocity of each radar candidate to a two-dimensional velocity vector, following the direction of the detection itself. Lastly, we use the attention mechanism to predict the association weight for each pair of detection and candidates, and achieve a more robust velocity estimation via weighted sum of all candidates. Compared with output fusion that operates at high-level tracks, attentional fusion fully exploits information from all radar measurements. So far, we have reviewed 3D perception from 3 different sensors. In self-driving, there's also a lot of prior knowledge that we can use to improve system robustness. One such example is high-definition maps. HD maps provide two types of prior knowledge: the 3D geometry of the environment and the roadmap semantics. In terms of 3D geometry, many works exploit the ground surface for more robust perception on hilly roads. Specifically, the height of each 3D LiDAR point is subtracted by the height of the ground so that it becomes invariant to the road slope. The ground surface can be parameterized as either a plane or in a pixel-wise dense format, which is more generalizable. We can either build the map offline and query it online, or directly estimate the ground geometry online with RANSAC or neural networks. Apart from geometry, HD maps also contain rich semantic information about the roadmap. One representation for this type of information is a raster image, where we rasterize the vector shapes of road elements as well as actual trajectories, and use different colors to encode different semantic meanings, such as lane types, orientation, and motion. A 2D CommNet is then applied for high-level feature learning. The raster representation is easier to implement and extend. However, they suffer from lossy rendering, limited receptive field, and intensive computation. A more intuitive and native representation is a lane graph, where we preserve the original vector format for lanes as well as trajectories. We then apply a graph neural network to obtain polyline level features, and another graph neural network to model interactions between lanes and agents. The lane graph representation doesn't have information loss, can capture larger and more structured receptive fields, and is more parameter efficient in feature learning. However, instead of resorting to different colors, now we need to delicately design the node and edge features of the lane graph so that they capture the full semantic information contained in the HD maps. So far, we have seen algorithms that focus on a few predefined categories of interest. However, the ability to recognize unknown objects is also critical for safe driving. One way to address this challenge is to explain every point in the LiDAR point cloud. In particular, our goal is to segment everything in the scene and classify it as either one of the known classes or as unknown. Additionally, we also want to recognize stuff, such as the road. One approach to tackle this task is shown in the figure below. The main idea behind the model is to project the LiDAR points into a category-agnostic embedding space. Then, within this embedding space, we can group the points into both known and unknown things and stuff, irrespective of their semantics. This brings us to the end of our session. Today, we have reviewed several techniques for 3D perception from 3 different sensors, as well as HD maps. We have also discussed the different input representations, detection frameworks, and sensor fusion mechanisms. Moreover, we have briefly touched on how to speed up computation and handle objects from unknown classes. We want to emphasize that there are still many aspects of perception for self-driving that we haven't covered due to time limitations. For example, perception from other sensors, such as ultrasonics, image and point cloud segmentation, and many more. Thank you for your watching.